Okay, this section 8.2 begins the actual process of us trying to construct these confidence intervals for population proportions on our own here. And one of the most important pieces to this process is that we have checked the conditions. And there are actually three conditions that you have to kind of check off before you can go about creating your confidence interval. The first one is making sure that somewhere in the problem it was mentioned or identified that the data was collected from some random process, that it's a well-designed random sample, or if it was an experiment, that treatments were assigned randomly. We just need to make a statement that it was done at random. Okay. The second condition that needs to be checked is for normality, because if you recall, we're using these critical values, these z-scores, which are all based on the notion that we're dealing with a normal curve. Okay, now this section is going to focus on proportions, and so when we deal with proportions to check for normality, we are checking what we had called the kind of that large counts condition, which was the number in the sample times the p-value, it's the probability of a success, and then the number in the sample times essentially the probability of a failure. Okay, those values both have to yield numbers greater than or equal to 10 in order for us to conclude normality. Okay, I'll go ahead and mention this, but we're going to be focusing more on it in the next section. But the condition for normality for means, one of two things has to happen. Either has to be stated in the problem that the population distribution is normal. If that's the case, then we can conclude that the sampling distribution is normal. If we don't know whether the population distribution is normal, or we actually told that it's not, skewed or something like that, then we could cite the central limit theorem if the sample size is greater than or equal to 30. Please keep in mind that the central limit theorem has nothing to do with proportions. You have to use this large counts condition here to check off normality. Okay, and the last condition, and this is really what confirms independence, is what we had referred to as that 10% condition. And the 10% condition is us showing that our sample size is definitely going to be less than or equal to 10% of the population. Okay, and that again is just kind of based on the fact that if we're sampling without replacement, in order for us to conclude independence, we need to check and make sure we're not taking too much of a chunk of the population. Okay, so in regards to how this is going to look on the formula sheet, and it looks pretty generic. Right here is how the formula looks for confidence intervals on the formula sheet. And so when it has this statistic here, we know that with proportions, that's going to be our point estimator, a sample proportion, and we would plug in whatever point estimate we're getting for our sample proportion there. Okay, then on the previous notes page, we had started to look at how to get the z-scores. Those are linked, or those are the critical value, and those are basically tied to whatever our confidence level is going to be. Okay, and then lastly, the standard deviation of the statistic, if we're dealing with proportions, this is actually on the formula sheet. Okay, this is what we would use for the standard deviation, and these two pieces combined together right here make up the margin of error, essentially. Okay, so I want to look at this example here. It says, suppose that we want to estimate the true population proportion of people who like Star Wars. So we take a simple random sample of 200 people and find that 79% of the people in the sample like Star Wars. It says here, explain why you technically cannot calculate the standard deviation of the sampling distribution of p hat. Okay, now what that is, the standard deviation of the sampling distribution, that's this formula right here. Okay, if you look closely, this formula really requires that we know the parameter, the true proportion. Okay? When in fact, most of the time, statisticians don't know the parameters. They've taken a sample, and all they really have is a statistic. Okay? So what they know is they only know that 79% of the 200 people in the sample like Star Wars. And so what statisticians end up doing is, instead of being able to use the standard deviation of the sampling distribution for p hat, they end up using what they call the standard error for p hat, which, if you compare these two formulas, they look almost identical. We're just taking the, to calculate the standard deviation of our statistic, we're going to estimate that using the sample proportion value that we got. So we would plug 0.79 in as an estimate for the p, and so that's why you see the symbol replaced there with p hat. Okay, so you can see that that's actually how it's written right here. We're using the p hats in these two places here. And so I just want to do a really quick example just to kind of demonstrate why this is actually a really good approximation for the standard deviation of the sampling distribution for p hat. Okay, it says, suppose the true population of people who like the color red is actually 0.4. Okay, we're going to take a sample size 1,000, and we're going to use that to estimate the true proportion, because we're just going to act like we don't really know that the parameter is 0.4, and get a sample proportion of 0.35. Okay, so our p hat value is 0.35. Okay, we're told secretly that the true parameter is really 0.4. It says calculate the standard deviation of the sampling distribution of p hat. Okay, now that's a legit formula where if you really, really knew the true parameter, you'd have p, you do 1 minus p, and then you would divide by n, the number in the sample. This would come out to a value of 0.0155. Okay, now we're going to calculate what's called the standard error of p hat. Usually we just put an SE with a little p hat symbol there. Okay, very, very similar formula, only this time we're going to use the 0.35, 1 minus 0.35, and 1,000. Okay, look how similar these answers are. They end up coming out really, really close to one another. And so that's why the standard error of p hat is a really good approximation for the standard deviation of the sampling distribution for p hat. Okay, it is very, very close to that. Okay. Right, so I would like to walk through just kind of one example from start to finish for how to construct a confidence interval here. And before we do that, I just want to make sure that we are okay with creating these different z-scores. And we kind of touched on this a little bit in the last section, so I'm just going to kind of run over this real briefly here. I think we had used the table at the end of 8.1 notes to kind of grab what the z-scores would be that would enclose an 80% confidence interval. Okay, you're welcome to do that. I just want to show you again here how you could do this on the calculator. Okay, when you're given your confidence interval, let's say 90%, remember we want to enclose in between here 90% of the data. That means there's a remainder of 10% left. That would mean you'd have 5%, 5% essentially in each tail. So if you were to use the inverse norm feature on your calculator, you want to make sure that you would put really 5% in this first spot for the area. Okay, I just usually type in the remaining area divided by 2, and that gives me what would be in like one of the tails there. Okay. Now, a lot of times the 90% confidence interval, if you type it in, you would see this next number here in the decimal. But because it's kind of so close to being rounded up, they carry this one out to 3 places instead of 2. Okay, but that's all you do to get the z-scores for the confidence intervals. Okay. Okay, so here's the formula, which it was on the previous page here, for calculating this confidence interval. And a lot of times it's named this. I really like to call it a 1 proportion z interval. Okay? And the reason I like to refer to it as that is because that's how it's called on the calculator. Okay, and in a little bit, we're going to look at how to do some of this on the calculator, but you have to make sure that you are also very comfortable using this formula, especially multiple choice questions. Okay, so 1 stands for, we took one sample. Proportion stands for, this is the parameter that we're estimating. The Z is referencing the fact that we're using these critical values to kind of enclose in what the confidence interval is, and interval means confidence interval. Okay. All right, so let's look at kind of the process for this. The AP test kind of creates this process here of a 4-step process called state, plan, do, conclude. Okay, and I'm going to stop this video here and make one other short video that's going to pick up right where this left off for us to talk about this process and do just the very next example here.